So basically what we're doing is a catch-up video from yesterday, which is the physics revision of the 9th of December, the worksheets, in which I'll be taking you through the answers based on the marking scheme of our topics from topic 2 to topic 8. Topic 2, particle and radiations. Topic 3, the waves. Topic 4 and 5, mechanics and materials. Then topic 6 being further mechanics and thermal physics. Then we'll be talking about topic 7, which is the gravitational fields. And finally ending with our nuclear physics topic. Now this is our, based on the chapter of particles and radiations, this is our topic on the particles and antiparticles worksheet from Physics Maths Tutor. Now this is based on our first question here, which I will read to you, that the equation shows the interaction between a proton and negative caryon that results in the formation of X. Under the equation which you can see that our negative caryon reacting with the proton to give us a positive caryon, neutral caryon, in other words denoted by K naught, along with the particle X. Now basically what we have to do in this is that we have to identify that what is the charged particle, explain whether X is a charged particle. Now as you can see, when we come to balancing of our the baryon number, you can see that actually it is in fact it's actually as you said, it is a baryon, but it should be, X should be a negative charge. If I show you according to the marking scheme that X must have a negative charge, and obviously so to conserve the charge, and obviously X being a baryon, in other words it conserves the baryon number. Now moving on to our third part of the question, which says that strangeness is conserved in the interaction. Explaining your answer to the quartz structure of X. This is our fourth one. Now basically coming on to the fourth one, what they're basically saying to us to do is that the strangeness in this case to left hand side is -1, but the strangeness to right hand side without X is +2, and the strangeness of X obviously adding to this is -3. Resulting obviously thus SSS. Now the strangeness in this case is SSS, or you can say that the strangeness on the right hand side without X is +2 and the strangeness of X is -1, thus SDD. This is therefore the quark structure of X. You have written down UUD, but what I would suggest is obviously going with the marking scheme and obviously writing either SSS, or you can say SDD. Now moving on to our third one, it basically says that we have to state the quark structure of K minus, K positive and K neutral. That would be done by basically saying, as you were correct in saying, all of them are correct, that the K minus is anti-US, K positive is U anti-S, and K naught, that was a neutral, is D anti-S respectively. Moving on to our second question. The second question states that a positive caryon K positive has a strangeness of +1. What's this quark composition of the K positive? You are correct in saying it's U anti-S, and whereas the up and anti-strange, obviously the particles. Then we come to the second question. What is the baryon number of K positive? Now, unfortunately, you were saying that it has a strangeness of +1, but the baryon number is in fact 0. As you can see that U is equal to our 2/3, and basically the S is equal to -1/3, but actually the baryon number of a K positive is actually going to be equal to 0 according to the marking scheme here. Then you can see that the third question is saying what type of antiparticle is the K. So what is the antiparticle of K positive? Well, it's actually a negative caryon with the quark composition, as you are correct in stating that it is anti-US. Now moving on to our third the B part of this question, that basically it's a tick and cross box type question, which should be this answer that they've basically stated in the case. Complete the table using the ticks and cross to indicate in the first row. You can see that the K positive has the lepton number is not present. However, in the case of the anti-muon and the muon positive, it has a lepton in there. As this is an example, it does not undergo the strong nuclear force interactions. And you can see the charged particle in this case, that the K positive, actually, obviously, it is a charged particle. However, the anti-muon is not a charged particle, but the muon positive is actually a charged particle. Hadron, it's under K positive. Yes, it is considered under the hadron particle, but in the case of the the muon neutrino and the muon positive, these are not considered as a hadron, as the hadron are defined as those particles or those states of matter that actually undergo the strong nuclear forces. Then moving on to our meson, we see that the meson is actually the K positive, which is meson and caryon, which come under this. So as you can see that yes, so the mesons are defined as those basically substances which do not undergo the these form the quark composition of our basically have the anti-quark composition in them. Now, however, the muon neutrino and the muon positive do not have a meson, respectively. Now, basically, we move on to the second question, which states that in this decay, charge, energy, and momentum are conserved. Give another quantity that is conserved in this decay and one that is not observed. Basically, the one conserved is the baryon number or the lepton number. However, the which is not conserved is actually our strangeness, or you can say the kinetic energy. Moving on to our part C question. This is actually should be yes. Now this confuses a lot of people in this case. That another possible decay of K positive is shown in the following equation. Identify X by ticking one of the boxes from the following list. When in fact the actual box should be a neutral pion actually, and this is confusing a lot of people. That actually should be neutral pion. Why? Because as there's no charge or zero charge that is actually observed, that in order to obey the conservation laws, or you can say cannot be a baryon to obey the conservation of the baryon number. As we know that the caryon quark composition is our U anti-S, which gives us obviously 1, and then the pion. Well, the pion is basically that will lead to it being +1. So in order for the +1 to +1, it should +1, then moving on that side -1, it will lead us to the formation of 0. So therefore stating that X should be 0, or it should be a neutral pion respectively. Now, basically moving on to our question number 3 in this case, that we have to, this is a very, very important question, that how it says complete the table to show the 4 fundamental forces and the corresponding exchange particles. ये आते exam में कि how to write this. Now, basically, what the answer should have been is it should have been weak nuclear, weak interaction, or weak nuclear interaction or weak force, which you have added in there. And the B question, in other words, that how does this take place, is our in fact the presence of the charge or the electric charge. In other words, name the physical quantity that a particle must have for electromagnetic force to act on it. This is in fact our charge, or which you said photon, but I would say right, the electric charge. Number C, Name the particle believed to be responsible for mass. Now, actually, this, if you look in your book in the case of conservation law, this is in fact the Higgs boson or the Higgs particle, respectively. Higgs boson particle. Now, we come to question number 4 then. Relatively easy question. Under certain circumstances, it is possible for a photon to be converted into into electron and a positron. State and explain what this process is called. This is known as a pair production process. Now, this is where the question which trips up a lot of people, in fact, is how to calculate the energy. Now, basically, this is a common formula which is used. The energy is equal to 2 times the rest mass energy. Basically, the energy of a photon, which is equal to 2 times, in the case of, this is our charge of the electron, which, as you can see here, is our 0.510999, which gives us an example of 1.021998 mega electron volt. Gives us the energy, and obviously we have to convert this into our joules, which gives us an answer of 1.6110 raised to minus 13 joules. Now we come on to question of the C question. Now we come on to question C. Basically, question number C states that a photon of a slightly higher energy than calculated in part B is converted to electron and a positron. What happens with the excess energy? Basically, what happens with the excess energy is the kinetic energy of this, obviously, is in the presence of the kinetic energy. In other words, this is the kinetic energy which is present. And as you were right in saying that actually this will lead to the annihilation of matter. What happens when a proton is in other words leaded with shortly after its creation, that actually, as you were correct in saying, the positron emission tomography, this works on the process of our annihilation of the matter. This actually results in the conversion of when a positron and an electron combine or collide, which lead to the production of 2 photons in the form of gamma radiations, respectively. Now, moving on to our question 5. Again, this is a very, very important question which you should know. This is basically how to attempt the answer. Now, as you can see, you've got the proton, which has the core composition of UUD. Then you can say the charge on a proton, which is +1, and the baryon number is actually 1. Then you see a sigma particle. Well, the sigma particle, the straightness on sigma particle is in fact -1, and the baryon number should be 1. Pion with the composition of UD, in fact, this is known as to have our positive pion, and it has a charge of +1. However, and obviously, as you can see, the strangeness and the baryon number is 0. Moving on to our question number 6. Each of the particles basically in the table has an antiparticle. Give one example of a baryon particle and its corresponding antiparticle. Now, this was basically very nicely done from your side in the case of it was that actually this is the question which examples of the proton and the antiquark. So you could say proton and obviously the antiproton, you can say, and consists of the 3 antiquarks. In other words, like this example, what I have shown to you. Now we come on to question number 6. Question number 6 is very, very important. This is our last question of the actual topic of the question paper. Now, we see on this that the pair production can occur when a photon interacts with matter. Explain what is the process of pair production. Basically, according to the Markov scheme, it says that pair production is defined as such a process when a photon interacts with the orbital electrons, or you could say the nucleus or atom. The energy of the photon is used to create the particle and antiparticle pair. This results in the conservation of momentum photon, which needs to in other words, to conserve the momentum of the photon, needs to interact with the interacting particles. In other words, it needs to interact with the case of our the positron and the electron, in other words, to conserve the momentum. Basically, what does B say? Explain why pair production cannot take place if the frequency of a photon is below a certain average frequency. Or basically, the energy of the photon, which you can say is that the energy of the photon is actually depends on the frequency. This is based on, in other words, which you wrote very nicely, which is based on the threshold frequency. Now, if the energy of frequency is below a certain value, there is not enough energy, in other words, to provide the mass or rest energy of the particles respectively. This is what you have to add in there, that you are correct in saying threshold frequency, but you have to develop your answer in saying that if energy or the frequency is below a certain frequency, there is not enough energy to provide the mass rest energy of the particles, which moves us on to number C. Basically, energy and momentum are conserved during pair production. State two quantities that must be conserved. This is in the case of baryon number and strangeness. Very well done, you've got these correct. But you can also do the other cases that you can add either charge or strangeness respectively.